Good day, everyone. We will present to you our topic about cooling systems, feed water heaters, condensers, and evaporator. It will be presented by Nise Hinayas, Merie Joie Aranas, Kristine Cambalon, and Revilla.
What is cooling system? Cooling is the transfer of thermal energy from one medium to another. In industrial applications, cooling can be critical to ensure that processes do not cause equipment or products to overheat. Many cooling applications use water as a medium to absorb heat because water has a high boiling point and high specific heat. Most of the water is used for cooling. Power plants boil water to produce steam, which is used to spin the turbines that generate electricity. Then, staggering volumes of water are withdrawn from nearby rivers, lakes, and oceans to cool the steam back into water so it can be used to produce more electricity. Why is cooling system necessary? Thermoelectric power plants boil water to create steam, which then spins turbines to generate electricity. The heat used to boil water can from burning of a fuel, from nuclear reactions, or directly from the sun or geothermal heat sources underground. Once steam has passed through a turbine, it must be cooled back into water before it can be reused to produce more electricity. Colder water cools the steam more effectively and allows more efficient electricity generation. There are many different ways to set up an industrial cooling system, but the three basic types can be summarized by examining how cooling water is used in each system. The three types of cooling systems and how they work. First is once-through cooling system. In once-through cooling, water is pumped from a nearby source and passes only once through the system to absorb process heat. It is then discharged back into the original source. This source may be a river, lake, ocean, or well. The average temperature change is 5 to 10 degrees Fahrenheit or 3 to 6 degrees Celsius. And the amount of water used is high. For examples, potable water systems, processed water, and general service. In the design being shown, it is common where large volumes of low-cost water are available. Additionally, these systems are typical when cooling demand is low to moderate. Processes are not critical and there is room to accommodate large equipment and high volumes of water. One drawback to once-through cooling is susceptibility to disturbance by stochastic water events, such as flooding. Moreover, these systems are being phased out due to concerns about water quality and conservation. The second type of cooling system is closed recirculating system or dry cooling tower. In closed recirculating systems or dry cooling towers, heat absorbed by the cooling water is either transferred to a second coolant or released into the atmosphere. The word dry is used because the water is never exposed to the air, and as a result, very little water is lost. An automobile engine is a good example of a closed cooling system. The average temperature change is 10 to 15 degrees Fahrenheit or 6 to 8 degrees Celsius, and the amount of water used is negligible. For examples are automobile radiator, chilled water systems, and food temperature controllers. Evaporation is not used in closed recirculating cooling towers. Instead, cool air rushes over a series of small tubes containing circulating coolant. Heat is transferred from the hot liquid inside the tubes to the cool air, resulting in cooling, and the coolant is then returned back into the engine. The last type of cooling system is open recirculating system or wet cooling tower or evaporative cooling tower. Open recirculating cooling systems or wet cooling towers are the most widely used designs in industry. Just as in closed recirculating systems, the open system uses the same water over and over again. Its most visible feature is the large outer cooling tower that uses evaporation to release heat from the cooling water. Due to the mechanism, this type of cooling tower is also called an evaporative cooling tower. And this system consists of three main pieces of equipment: the recirculating water pumps, the heat exchangers, and the cooling tower. The average temperature change is 10 to 30 degrees Fahrenheit or 6 to 17 degrees Celsius, and the amount of water used is moderate. For examples are cooling towers and spray ponds. How wet cooling towers work? Open recirculation cooling systems features wet towers where cooling water comes in direct contact with upward airflow. Water from the heat exchanger is pumped evenly over the top deck of the cooling tower. It cascades down and is broken into tiny droplets as it passes through a series of splash plates called cooling tower fill. This fill can be corrugated plastic sheets, wooden slats, or other devices that increase surface area, thereby enhancing evaporation. As the water droplets bounce off the cooling tower fill, the hottest molecules break away from the water and are carried up and out of the tower as drift. The remaining cooled water collects in a tank at the bottom of the tower called the basin. This cooled water can now be pumped back into the heat exchanger. Cooling systems rely on water as a heat transfer medium. This means that water quality becomes essential for continuous operation of any cooling system.
Okay, we're going to go through the cooling system. So out here in the generation room, we have two pipes, coolant mains. The upper pipe is the hot coolant from the engines going to the radiators. The lower pipe is the return coolant coming back from the radiators to the engines. Okay, we're in the radiator room. We're going to continue looking through the cooling piping system. So again, we have the hot coolant piping coming across the top, the coolant return down low. Now I want to point out on the piping system, here we have some typical butterfly valves. These are quarter turn valves. Generally, if the handle is pointed parallel to the pipe, it's in the open position. At 90 degrees to the pipe, it's closed. These valves have small tags on them. The NO tags indicate a valve that is normally open. And then here we have an NC tag that indicates that the valve is normally closed. So it's really important in the piping system to become familiar with the valves and their function. So then, continuing on with the tracing of this piping, we have the hot coolant piping comes across, up and over the top of the radiator. Above the radiator, we have an isolation valve on the top. So each radiator can be valved off separately if it needs to be serviced. We also have an air bleed line on top of the radiator to allow us to get the air out of the top of the radiator tank. Then on the bottom, we have the return piping that comes out the bottom, and then there's another isolation valve down below. There's also a drain valve there that allows us to drain down the radiator when it's valved off to be serviced. And then in the return piping, we have a thermometer, and this allows us to be able to monitor the temperature coming back in the piping from each radiator. Now, the other part of the piping system in every cooling system is the expansion tank. And over here we have a glycol expansion tank mounted up high on the wall. It has to be mounted up high to give us positive pressure on the system. This expansion tank allows the glycol to expand and contract as the temperature goes up and down. Under normal operating conditions, it should be about 2/3 full. So you can look at the sight gauge. That's part of the daily check. Make sure you're up about 2/3. If you get a little low, there's a point here for adding glycol. Now I want to make note here, this valve is tagged, normally closed, open only for adding coolant, ethylene glycol only. You have to add the same brand and the same mixture of glycol to the system as what is already installed. So you need to make sure, verify what is in the system, and then only add the same product. And generally, this should be bought pre-mixed, usually 50-50, sometimes 60-40, with a treated water. You don't ever want to add local water to the system because the minerals in it can clog up the cooling system. So to add glycol, you would just open the valve here, put the hose in the barrel, hand pump it till you get back up to your 2/3 level, shut the valve off. And that's how the cooling system works. Now we're going to go through the operation of the radiators themselves. Okay, each radiator is ducted out the wall. Where it penetrates the wall, we have a motorized damper. When the radiator is not operating, this damper is closed. Then when the radiator operates, this little motor operator turns 90 degrees, opens the damper to discharge the air out through the wall. Associated with each radiator is an air intake damper. Same thing, the duct through the wall has a motorized damper on it. When the radiator operates, this damper opens to allow fresh air to come in for cooling of the radiator. And we've installed filters on these intakes that cuts down on the bugs and the dust that's brought into the room. Now the radiators are controlled by a variable speed drive. So for each radiator we have a separate panel, and we'll go through the function of those panels now. So this is the variable speed drive. What this device does is it controls the speed of the radiator fan to meet the cooling load. Just speeds it up, slows it down as the load varies. So we're going to go through normal operation. This is the main breaker, on-off switch. This should always be left in the on position. The only time you would ever turn it off is if you had a failure and you need to work on something. So when it's on, then we have a green power on light. There's a control mode, which is normal and test. The test mode is only used for a technician when they're trying to program the panel, so you should never turn this to the test mode. Just leave it in normal. Then over here we have a VFD mode, off, and bypass. Again, you would only turn it off if you needed to work on something. Otherwise, it stays in the VFD mode. That allows it, VFD stands for variable frequency drive, allows it to speed the fan up and slow it down. We have a VFD fault. In the event that the VFD device itself fails and we get an alarm and it quits working, we have a bypass mode. In the bypass mode, it turns the fan to full speed and it just runs continuous. So if you had a failure of the control device for some reason and you were overheating, then you could turn it into bypass mode on a temporary basis, and that would run and provide cooling. So I'll demonstrate how that works. When we go to the bypass mode, we'll hear the fan ramp up to full speed. Okay, sometimes when the VFD is first turned on or turned from the off to the VFD position, we'll get a short light and a little alarm. That's just kind of a normal part of the powering up procedure, and it's nothing to be concerned about. So after a moment it clears. We're back in business here. We have our VFD mode, power on, and this system is clear to operate. Okay, now one other thing I want to note here is that typically when we have a 2-radiator system, we will set the set point about 5 degrees apart, 5 to 10 degrees apart. In this case, we have the first radiator set to operate at 175 degrees, so it will come on first, and then the second radiator at 180. So in times of low load, it's very common to come in and see only one radiator running. Then if your load increases on a hot summer day, you might see the second radiator come on. But that's called a lead lag function. So one radiator takes the lead, runs first, and then when it can't meet the cooling requirements, the second radiator comes on.
What is feedwater heater? A feedwater heater is a power plant component used to preheat water delivered to a steam generating boiler. The source of heat is steam bled from the turbine, and the objective is to improve the thermodynamic efficiency of the cycle. Preheating the feedwater reduces the irreversibilities involved in the steam generation. This reduces plant operating cost and also helps to avoid thermal shock to the boiler metal when the feedwater is introduced back into the steam cycle. Feedwater heaters Feedwater heaters are heat exchangers designed to preheat boiler feedwater by means of condensing the steam extracted from a steam turbine. It is used in a regenerative steam cycle to improve the gain. This figure shows the different parts of the feedwater heater.
Here's feedwater's composition, as following steam inlet side. There are baffles in D superheating zone, support plate, baffle in drain cooling zone, pressure safety valve, and vent nozzle. For tube side, feedwater inlet nozzle U-tube, outlet nozzle.
Why use a feedwater heater? What are the importance? Feedwater heaters serve a number of purposes, all of which provide significant cost savings and environmental advantages. First is to reduce fuel required for combustion by increasing the initial water temperature to the boiler. Second, to reduce heat losses in the condenser. Third, to minimize thermal transients within the boiler. Fourth, to lower emissions as fuel used to reduce due to improved heat rate. Fifth, to improve overall efficiency of the plant. Sixth, to reduce operating cost and ease thermal stress on the boiler. Feedwater heater design. Most of the feedwater heaters are shell and tube design, in which a bundle of tube stack is contained within the outer shell. U-tubes are the most common tube bundle configuration as they are relatively resistant to the thermal expansion during operation. In most configurations, the feedwater flows inside the tube side and the steam flows over the cell side. The materials of the tube inside are made up of copper alloys and non-ferrous metals for the low and high pressure heaters tube. For low pressure heater tubes, copper alloys are extensively used. These alloys have got excellent thermal conductivity, but on the other hand, those alloys have problem of copper carryover and ammonia attack, which may require a complex boiler cleaning after short intervals. To avoid all the problems, the stainless steel tubes are invariably used for low pressure heaters. Stainless steel is unaffected to all operating conditions, except that it is susceptible to chloride-induced stress corrosion. For high-pressure heaters, the most common materials are carbon steel, stainless steel, and Monel metal. This figure shows the two different positions of the feedwater heater. First is the horizontal. Horizontally mounted feedwater heaters occupy more floor space. However, most feedwater heaters are configured in this position as it provides the greatest stability in regards to water level control and offers convenient access for tube bundle removal. Second is the vertical. Vertically mounted feedwater heaters conserve floor space, but there is reduced control volume available for liquid level fluctuation. Vertical channel down. This assembly is by shell removal. Installation and removal is likely to be more difficult than for horizontally installed feedwater heaters. Vertical channel up. It is the least frequently used feedwater heaters. This assembly is by bundle removal. If a sub-cooling zone is present, the zone must extend the full length of the bundle, as the water must enter at the bottom end and exit at the top end of the feedwater heater. Most of the power plants used horizontal mounted feedwater heaters. According to inside zone type and number, feedwater heater sort 1 zone, 2 zone, or 3 zone type. This figure shows is for 3-zone feedwater heater. First is the condensing zone. The condensing zone is the major internal section of all feedwater heaters. It is a large amount of tube surface area held in place by tube support plates, condenses all the incoming steam and additional steam produced by flushing of incoming drains, if any. In the process of condensing the steam, entrained non-condensable gases must be continuously removed in order to prevent blanketing of surfaces, resulting in loss of performance and corrosion. Second is the subcooling zone. The drain subcooling zone reduces the temperature of the drains, leaving the condensing zone below the saturation temperature by transferring heat to the entering feedwater. Third is the de-superheating zone. The de-superheating zone removes a portion of the sensible heat of the superheated extraction steam to elevate the temperature of the feedwater.
First, feedwater is flown into the tube through feedwater inlet nozzle. As steam is flown in through steam inlet nozzle, the steam inside the shell exchange the temperature of feedwater to continually increase. Non-condensate gases, which decreases the performance of the feedwater, are released. Keep the nozzle opened while operating the feedwater heater through vent nozzle.
Feedwater heaters can also be open or closed heat exchangers. There are two types of feedwater heater. First is the open feedwater heater. For open feedwater heater, the extraction steam is mixed directly with incoming sub-cooled feedwater to produce saturation water at extraction steam pressure. Second is the closed feedwater heater. For closed feedwater heater, steam does not mix feedwater with the compressed water from the pump. It is typically a shell and tube heat exchangers where the feedwater passes throughout the tubes and is heated by turbine extraction steam. Feedwater heaters are classified as low and high pressure heaters. This item is installed to improve power generator efficiency by heating supplied water and reducing breakage due to heat stress from temperature differences in boiler tube. First is the low pressure feedwater heater. It is basically simple straightforward tube and cell heat exchangers, with a condensate passing through the tubes and the bled steam being admitted to the shell. Next is the high pressure feedwater heater, also generally of traditional form but are arranged in a horizontal attitude to ensure free gravity drainage of their bloodstream lines and heater-to-heater drainage. Many power plant operators have begun replacing outdated level instrumentation with the newer technologies to accurately control feed water heater levels and decrease their plant's heat rate. However, assurance of proper performance can only be determined with a feedback reporting system in place. There are three primary parameters used to monitor individual feed water heater performance. First is the feed water temperature rise. It is the difference between the feed water outlet temperature and the feed water inlet temperature. A properly performing heater should meet the manufacturer's design specifications, provided the level controls are up to the task. Second is the terminal temperature difference, or TTD. It provides feedback on the feed water heater's performance relative to heat transfer and is defined as the saturation temperature of the extraction steam minus the feed water outlet temperature. An increase in terminal temperature difference indicates a reduction in heat transfer, while a decrease is an improvement. Third is the drain cooler approach, or DCA temperature. It is the temperature difference between the drain cooler outlet and the feed water inlet temperatures. An increasing DCA temperature difference indicates the level is decreasing, whereas the decreasing DCA indicates a rise in level. What is the effect of adding more feed water heaters in the power plants? Well, the higher the feed water temperature, the less fuel is required to produce the steam used to produce electricity in the steam turbine. However, steam is extracted from different locations on the steam turbine to heat the feed water heater, which increases the power plant heat rate.
What is condenser? Condenser is a large heat exchanger designed to cool exhaust steam from a turbine below the boiling point so that it can be returned to the heat source as water. Condenser is an essential component of a modern steam condensing plant. It is a closed vessel in which high pressure steam from the steam turbine condenses into low pressure. The pressure inside a steam condenser is kept below the atmospheric pressure to increase efficiency. It is generally used for lowering the back pressure of the exhaust of the turbine end. In power plants, condensers act as a heat rejection engine when condensing steam into water. The volume collapse of that conversion causes a significant pressure change, creating a vacuum that pulls steam through the turbine. Because the heat transfer of the condenser drives the back end of the water-steam cycle, the efficiency of that heat exchange is crucial to optimizing the extraction of energy from the steam. In thermal power plants, the purpose of a surface condenser is to condense the exhaust steam from a steam turbine to obtain maximum efficiency, and also to convert the turbine exhaust steam into pure water, so that it may be reused on the steam generator or boiler as boiler feed water. It reduces back pressure of the steam, which results in more work output. It reduces temperature of the exhaust steam, which also results in more work output. The condensed steam can be reused as feed water for boiler, which reduces the cost of power generation. The function of the condenser is to condense exhaust steam from the steam turbine by rejecting the heat of vaporization to the cooling water passing through the condenser, and to maximize turbine efficiency by maintaining proper vacuum. Once the steam has passed through the turbine, it enters the condenser where heat is removed until it condenses back into liquid water. This is done by passing the wet steam around thousands of small cold water tubes. The cold water is usually supplied from a nearby sea, lake, river, or from a cooling tower. The condensed steam is collected at the bottom of the condenser and returned to the boiler using feed water pumps to begin the water to steam to water cycle again. The temperature of the condensate determines the pressure in the steam or condensate side of the condenser. This pressure is called the turbine back pressure and is usually a vacuum. Decreasing the condensate temperature will result in a lowering of the turbine back pressure and increasing turbine power output and efficiency. As the operating pressure of the condenser is lowered, the enthalpy drop of the expanding steam in the turbine will also increase. By lowering the condenser operating pressure, the following will occur. Increased turbine output, increased plant efficiency, and reduced steam flow. Condenser has the following secondary functions. It is collected in the condenser hot well, from which the condensate pumps take their suction. Provide short-term storage of condensate. Provide a low-pressure collection point for condensate drains from other systems in the plant. Provide for the aeration of the collected condensate. A typical power plant condenser has the following functional arrangement. Large power plant condensers are usually shell and tube heat exchangers. These types of condensers are also classified as single pressure or multi-pressure, depending on whether the cooling water flow path creates one or more turbine back pressures. By the number of shells, as either single pass or two pass, depending on the number of parallel water flow paths through each shell. The parts of shell and tube condensers involved in the transfer of heat from the steam and condensate to the cooling water should have the following properties. Be resistant to corrosion from both the steam or condensate and the cooling water. Have a minimal resistance to the flow of heat from the steam or condensate through the material into the cooling water. Provide mechanisms to remove organic and inorganic deposits on the heat transfer surfaces in contact with the cooling water. Inefficiencies caused by a variety of issues can creep into the condenser and lead to power production losses, higher production cost resulting from higher fuel usage and cost, lower environmental performance from carbon dioxide emissions, reduced profit margins. Significance of condensers. Condenser gives the vacuum needed for steam to exit spontaneously from the turbine. Without vacuum, the steam will find it difficult to get out of the turbine. Condenser helps to recover the high quality working fluid. Without condenser, we would be losing pure water as steam exiting the turbine into the environment. Actually, purifying water is a tedious and energy-intensive process. We cannot afford to purify water throughout to compensate for exhaust steam. Thus, we prefer to have pure water locked in the cycle and recover it from steam for each and every cycle at the expense of the latent heat. Efficiency improvement for condensers. Condenser is a heat source as well. It can be used for heating application. This would increase the overall efficiency of the plant. If you could maintain low pressure at condenser, the expansion of steam will be greater in turbine. Thereby, the work done will be more. Without condenser, pure water requirement will go up and hence a major portion of energy generated will be used for purifying water itself. This would greatly hurt the overall useful output attainable from the plant. The exit temperature of condenser is considerably large compared to the water temperature available in water sources. Without condenser, we will be using the fresh charge of water all the time and hence will be losing the sensible heat saving. Thus, condenser improves thermal efficiency of the plant.
This is a cooling tower. Its main use is to lower the temperature of the used water in the power plant so it can be reused again. There are a lot of misconceptions or false information about these towers. In the UK, two-thirds of the people believe that the smoke or harmful emission that emerge at the top of the tower can accelerate climate change. It's actually called drift, and you'll often see drift coming out of the top of natural draft cooling towers. It looks like smoke, but it's actually just evaporated cooling water. Some people believe that the emission is toxic and can cause illness to the surrounding community. This is not true since the emission is just water vapor, but there is a possibility of bacterial growth inside the cooling tower. These bacteria can be carried up by the drift, which can cause illness to the surrounding area, just like the incident in France that killed 28 people. This rarely happens since the water quality is regularly checked and a dose of biocide is applied regularly. A cooling tower is a device for cooling large quantities of water, which circulating in a water recycling system. Circulating water system is a system in which water is used as refrigerant for cooling heat exchange equipment. The use of cooling water saves natural water from 25 to 50 times compared with one's true cooling system, and prevents thermal pollution of bodies of water. After cooling, 5% of water is lost to evaporation, drip loss, leakage, and discharge into blown system. Losses are replenished by fresh water makeup. The hot water is pumped out from the condenser into the inlet of the distribution manifold at the cooling tower. The hot water from the pump is pumped into the distribution manifold inside the cooling tower. The distribution manifold vary in design. If we focus on the natural draft cooling tower, the design has a main tube ring which goes around the entire tower, and it is connected by several smaller pipes across its diameter. Once all distribution pipe is charged with hot water, it will pass through the second part of the distribution manifold, which is called spray nozzles. The hot water inside the pipe will impact the end of the nozzle, which will create a circular spray pattern. All the nozzle will create this circular pattern, then the water will drip into the surface of the field. On the fields, a thin film of water is formed on the surface. While the hot water is dripping on the surface of the field, evaporation will occur. It is due to the air in the surrounding. The larger the surface area of the fields, the more intensive is the evaporation of water, and the more efficient is the cooling tower. At the tip of each field, a water droplet is formed, which has a lower temperature than the water that enters the cooling tower, or the water distribution manifold. Then, it will drop into the basin, which is pumped back to be used in the plant. There are two common types of field: the thin film and the splash bar. There are three kinds of cooling tower based on the fan. The first one is forced drop cooling tower. The fan is installed at the bottom or below the field, and it is rarely used. The second one is called induced draft cooling tower. The fan is installed at the top of the field, and it is always used for small power plants to maximize the efficiency. The last one is called natural draft cooling tower, also known as natural convection cooling tower or hyperboloid cooling tower. This kind of cooling tower is often seen in thermal power station like coal-fired power station and nuclear power station. And that is simply because natural draft cooling towers are expensive to construct, and these are only used if there is a large cooling requirement for a very long period of time. Natural draft cooling towers rely upon the principle of stack effect, also referred as chimney effect. To understand the concept of cooling towers, we need to understand the process of evaporative cooling. The water is being sprayed out of all these nozzles. It is sprayed over a very large cross-sectional area, and it slowly drips through the field. A lot of water come into contact with air. Some of the water is going to evaporate. When it evaporates, it's actually gonna cool the water molecules surrounding it. This process is called evaporative cooling. When this occurs, the water that drops out is actually cooler than when it originally entered the top of the field.